So we are now moving into the thermodynamic unit, which is the second to last of the major topics that we have to cover this semester. And you're going to notice that there's quite a bit of a throwback to the thermochemistry unit, among other concepts as well, but especially thermochemistry because we deal a lot with energy. So we're going to be talking in this lecture about what you call entropy and the thermodynamic favorability. So let's go ahead and get moving. The first thing to talk about is the first law of thermodynamics. And we talked a bit about this at the beginning of the thermochemistry unit last semester, where we talked about the law of conservation of energy, which is that energy is conserved. So that is the big idea of thermochemistry. When you say that the Q, I'm going to write this down again just to remind you that the Q of the system is equal to negative Q of the surroundings and vice versa. So what that's saying here is that energy is neither created or destroyed. You can't create it, you can't destroy it, you can transfer it from one substance to another substance. So that's why in calorimetry, we assume that the energy given off by the system is absorbed by the surroundings and vice versa. Now the change in energy, we talked last semester how Q refers to the heat and W refers to work. So if the value of Q is positive, that means that the system, we're assuming that energy refers to the system, that Q for the system is absorbing heat, and if Q is negative, the system is going to be going down and releasing some of that heat, and that's going to make the value of delta E smaller. Okay, now when the system does work, then the delta E will be negative because W would be negative. And then if work is done on the system, W will be positive, and therefore the value of delta E will be higher. And you don't really need to know about what exactly work means. That's more of a question that you do in physics. And that's not going to be a huge idea behind the AP test, but we do want to make sure that you understand that energy refers to the amount of heat and the amount of work, or at least the change in energy refers to the amount of heat and work done by the system or on the system, etc. So moving on forward here, we're going to talk about what a state function is, and that is referring to properties of the system at that moment. So we can say that temperature, energy, the heat content, and you will soon learn about S, which refers to entropy. Those are all properties of the function at that given moment. So if we state that the temperature is, say, 25 degrees Celsius, 298 Kelvin, and we're saying that that's the property of the system at that moment. Same with the heat, when you say, the delta H, which is enthalpy, when you're saying that the enthalpy of a system is, say, 50 kilojoules, you're saying that the system has a heat content of 50 kilojoules. Okay, now be very careful that you don't think of Q and W, because Q refers to the amount of heat that is being transferred from the system to the surrounding, and vice versa. And W refers to the work being done on the system or by the system. And those aren't properties that are intrinsic to the system, so we do not consider them to be state function. Okay, that said, though, do you say that the amount of heat gained or lost by a system is equivalent to delta H, which is the change in enthalpy of the system that's in question. And that's the very definition of what the change in enthalpy means, is that it's the heat content, the change in the heat content of the system. Okay, so the main thing, one of the main ideas behind this chapter is the difference between thermodynamics versus kinetics. Thermodynamics deals with the question as to whether a reaction can happen. And we say spontaneous, or more accurately, thermodynamically favorable, to talk about whether a reaction will happen and to what extent it will happen. Okay, kinetics, which you learned about at the end of last semester, deals with the speed of the reaction. So something can happen, but it can, and that would be a idea of thermodynamics. But if it happens quickly or slowly, that's a function of kinetics. Okay, so an example of this would be, let's talk about the process of rusting, which is 4Fe solid plus 3O2 gas yields 2Fe2O3. Okay, I'd like you to think about it. Think about whether rusting happens very quickly or very slowly. If you think of a piece of, let's say you take a paper clip, and you set it out on your desk, and you observe it. And you'll notice that it's happening, it is definitely reacting with the oxygen in the air, but it's happening at a very slow rate to the point that it is not really observable. But if you let that paper clip sit there for, maybe a year, 2 years, 3 years, 4 years, or a really long time, eventually you'll see that it's rusted, but it's not really happening at a rate that you can see it happening in real time. Okay, so the fact that it is rusting means that it is thermodynamically favorable, but the fact that it's happening slowly indicates that that is the function of kinetics. And the reason why it's happening so slowly is because if you look at the reaction profile diagram for rusting, which happens to be an exothermic reaction, okay, you can say that the activation energy of that, we call that EA, is very high. Okay, it's still going to happen, but it's going to happen very slowly. And so when we say it's going to happen, that means that it's thermodynamically favorable. Okay, so again, make sure you understand the distinction between thermodynamics versus kinetics. So this brings us to one of the key ideas of thermodynamics, and that is what you call entropy, not to get confused with enthalpy. Okay, entropy, for a really simplistic and not altogether correct definition, that would be referring to the amount of disorder, but you don't really want to say that on the AP exam. Really, entropy, you have to think about it from a probability standpoint, and probably a better way to think of it as would be the number of microstates available. Okay, and I know that's going to be kind of a hard definition to wrap your head around, but when we say about a number of microstates, we're referring to the arrangement, okay, that are possible, like possible arrangements. And that would be considered to be a state function, because we're talking about at that given moment what the properties of the function, how many arrangements does it have possible in that state function. Okay. A positive value for delta S for entropy usually refers to thermodynamic favorability, which means it is likely to happen. And we'll talk more about that in a moment. Okay, an example of an increase in entropy, for example, let's take a look at this one. If you see a solid, and I'm going to draw 10 molecules together, 4, 5, 6, 7, 8, 9, 10. Okay, versus, and let's say it's going through a sublimation process. Let's say it's going to a gas. Okay, and then when it's in a gas, you can see that there is a lot more chaos in the second diagram. 3, 4, 5, 6, 7, 8, 9, 10. There's a lot more chaos going on here, which means that the gas particles can be arranged in many, many more ways possible than they can be arranged in a solid state. Okay, so when they're in a solid state, they're packed very tightly together. There's less room for variability. Whereas, for example, with the gas phase, this particle right here could be over here, over here, over here. This particle could be over here, over here, over here. But in a solid state, they're much more limited. So in this case, the first diagram would be considered to be lower in entropy because it has fewer microstates available. Okay, the second diagram is higher in entropy because there are more microstates available, more possible arrangements for the gas particle. And that's why you can see that as maybe disorder is a way to indicate that, because a solid has far less disorder than a gas does. But really, a better technical definition of what entropy is referring to the number of microstates possible. And greater entropy signifies that you have a greater number of microstates possible at that moment. So that brings us into the second law of thermodynamics. And unlike energy, the entropy is not conserved. In fact, for any process that is happening, for any process that is spontaneous, for any process that occurs without any assistance, we want to say that the entropy of the universe, which includes the system and the surroundings, must always increase. And I can say always because this is one of the laws of thermodynamics. Okay, so what it's saying here is that you may reduce entropy in one area, but that's going to increase entropy overall in another area. And it's going to increase it by a lot more than the decrease in area in entropy in the other area. And I will talk about that in class, probably in a bit more detail to explain to you more what I mean about that. But even if you reduce, so if a process happens to occur, if I reduce the entropy in the system, the surroundings will increase by much more, so the universe entropy will increase. Okay, or if the system increases in entropy and causes a decrease in the surrounding, that would still lead to an overall increase in the delta S of the universe. Okay, so for any thermodynamically favorable process, the delta S for the universe is always going to be positive. And that's something we'll be exploring more in class as you do the in-class thermodynamic problems that we'll be doing in the next week. And so as we were saying earlier here, a positive delta S tends to be thermodynamically favorable. And let's think about this. Let's say you have a deck of cards numbered 1 through 10. And let's say that you throw them all up in the air and then you collect them. And what are the odds that they're going to be in order? And you're going to say that's going to be very, very low. So it's easier to increase the amount of disorder to go from orderly card to disorderly card than it is to go from disorderly card to order card. So the universe tends to like disorder, and you can imagine why that would be the case. And so that's why a positive delta S for a reaction not always, but it tends to lead to greater thermodynamic favorability, meaning that it is more likely to happen. Okay, and so once again, we talked about how the delta S of the universe, the entropy, must be positive for a process to be thermodynamically favorable. And that's a key part of the second law of thermodynamics. Okay, so what does that bring us to? That talks us to how we can identify what the sign of delta S for the system would be. And in this class, I won't really concern you with that many questions about what the delta S of the sign of the universe is, but you should at least understand what the change in entropy is for a system. So if you take, for example, a block of ice, and let's say we go from H2O solid to H2O liquid, or if you go from H2O liquid to gas. As we talked earlier, there is a lot more arrangement possible in the gas state than there would be in the solid state. Okay, and then the liquid state would have more possible arrangement, more disorder than it would be in the solid state. However, gas particles tend to have even greater disorder, greater entropy than the liquid state does. So going from a solid to a liquid to a gas would lead you to a delta S that is positive. Okay. Also, a solute such as NaCl, going from a solid to NaCl aqueous, that would also have a value of delta S, because the particles, when they're in their solid state, again, will probably be very rigid and fixed and not moving a whole lot. Whereas when you put them in water, they'll dissolve and they'll break up, and they have a lot more disorder and a lot more arrangement possible. Okay, heating a system, you can imagine, would increase the kinetic energy, average kinetic energy that is. I may note that. Okay, which would increase the movement of the particle. And then once again, you have greater arrangement and greater disorder as a result, leading to a positive value of delta S. Okay, a decomposition reaction, such as, say, calcium carbonate, solid, leading to calcium oxide, solid, and CO2, also tend to have a positive value for delta S, as they would have more arrangement. And also a reaction that has more gaseous product particles than gaseous reactant particles, aka more gases being produced, then that would be an example of a positive delta S for the system. Okay, so take a moment to pause the video and see if we can read through each scenario and determine what the sign of delta S for that particular system is. All right, go ahead and look at your answers. And the first one has a positive value for delta S because you're going from a solid to aqueous. Again, more disorder, more microstates. The second one is negative because you're going from a gas to a solid. So there are fewer microstates happening, there's fewer amount of disorder. Okay, heating N2 gas increases the average kinetic energy, which makes the particles move faster, giving them more movement, which increases the number of microstates available. And the last one, you have both the amount of reactant particles decreasing as they go into the product, and you also have the amount of gas molecules also decreasing over the course of the reaction. So that, of course, would be a negative delta F. Okay, so that concludes that lecture.